All right, the last section in Chapter 5 that we're going to discuss talks about sampling distributions and the central limit theorem. I almost skipped the sampling distributions because it's going to get a little bit wordy. There won't be as many questions on your exam regarding that. What really is the meat of this section is this central limit theorem. So although I'm going to start with this sampling distribution, I don't want you to get bogged down in the terminology or bogged down in the confusion that it can create. It just adds a lot of data. Basically, it says the probability distribution from a sample is formed when random samples of size n are repeatedly taken from the population. So we're going to start with the population, and instead of being able to choose all the population, we're going to randomly choose different samples. The sample statistic is the sample mean, and then the distribution of the sampling distribution of the sampling means. Again, this is why it gets really wordy. If the sample statistic is the sample mean, then the distribution is the sampling distribution of sample means. Every sample statistic has a sample distribution. So again, that's just very, very wordy. Basically, what it's just saying is that we're going to take a whole bunch of random samples in this population. Some may overlap, some may not overlap. They each one have their own mean. So X1, X2, X3, X4, X5, they each have their own mean. But if we sample enough of these random samples, then it says the mean of the sample means. So the mean of all of these is going to be the population mean. And the standard deviation of all these standard means is going to be this new formula. So it's a little bit different formula. The standard deviation of the sample means is called the standard error of mean. So it's going to change, it's going to fluctuate our answers a little bit, but at the end of the day, it's really not that worrisome. So although there's an example here, I'm going to skip this for now. So we're just going to skip for now. And instead, we're going to go to where it really applies, which is the central limit theorem. Because what's nice about the central limit theorem is it says if random sizes of size n or greater, so n greater than or equal to 30, are drawn from a population with a mean, mu, and standard deviation of sigma, then the sampling distributions become the normal. So it approximates into the normal. So what it does is it allows me to have things that don't look, and if you look here, this almost looks like a bell curve, but it's off a little bit. But it says as long as our sample size is greater than or equal to 30, then I don't have to look at the blue part. I can say that it approximately is going to represent the same as the standard normal. And because it approximately represents that, then that's going to be nicer and easier because, of course, then we can go straight to the calculator and use our calculator. So that's all this means, is that it's going to be approximately that. All right, so if I read the rest of the standard of the central limit theorem, if random samples of size n are drawn from a population that is normally distributed, then the sampling mean is normally distributed for any sample size. Again, so it's just allowing us to use what we know about the standard normal in a greater context, where I don't have to have a perfectly bell-shaped curve. I can have these almost sort of bell-shaped curves, and it works the same. The mean of the sample is just a regular mean. What's going to be different, though, is when we find standard deviation, which we're still going to need, it's really going to be the original standard deviation divided by the square root of n. So x, the mean of the samples, that's what the x bar is going to be the mean of the original but the standard deviation of the samples is going to be the standard deviation of the original divided by the square root of n, remembering that n is the sample size. So you just have to do a little bit more work here, but not a whole lot, to make it so that we can change any misshapen data into the standard normal, provided we have enough size. So and 30 pieces of data is not very large, as you know, because that's a sample that we're going to apply to the entire population. So only needing 30 pieces of data is not all that much. All right, so example of the central limit theorem. A study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours. So mean is 6.8 hours. Standard deviation of 1.4. Random samples of size 100 were drawn from this population, and the mean of each sample was determined. Find the mean and standard deviation of the sampling distribution of the sample means. So n is equal to 100. Is that greater than or equal to 30? That's one of the things you have to make sure. N is indeed greater than or equal to 30. So we're good. I want to find the mean and the sample deviation of the sampling of these. So this is going to tell me that the sample mean is going to equal to the regular mean. And in this case, that would be 6.8. The standard deviation of the sample. So the X bar means sample. So the standard deviation of the sampling is equal to, according to the formula, the original standard deviation divided by the square root of n. So in this case, it would be 1.4 divided by the square root of 100. Square root of 100 is 10. So that's 1.4 divided by 10, which is equal to 0.14. So this is the standard deviation. So notice what it did. Because the standard deviation is less, it's going to make my normal curve just look steeper. There's going to be a little less variation in there, which is what standard deviation does. It tightens up the variation. So instead of having 1.4 hours, now we're only having 0.14 hours. So that standard deviation is going to tighten up a little bit. So if we looked at it on the curve, it's going to be a lot steeper. The mean is still 6.8. But now, when I go over one standard deviation, I'm only adding 0.14. So this would be 6.94. And if I subtract one standard deviation, so 6.8 minus 0.14 is 6.66. Just like this is 6.8 plus the 0.14 to give us 6.14. So it makes this graph tighter. It brings the data into it. So it's a little bit less as it applies to the entire population because we've squeezed and condensed the data into a smaller, steeper curve, if that makes sense. But like I said, the biggest thing is that we can apply everything we've learned with a very small number of data points. And that's awesome. All right, number 2. The training heart rate of 20-year-old athletes is normally distributed with a mean of 135, standard deviation of 18. So the mean is 135, standard deviation is 18. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Find the mean and standard deviation of the mean here. Right? So at first, you might think that because our size is 4, which is not greater than or equal to 20, that we can't do anything with this. However, if you reread the question closely, this says that we already are normally distributed. Since we already are normally distributed, it doesn't matter about the size. And that's the difference. So if you look at this first example, nowhere in here does it say that this study shows that they are randomly, that they are already normally distributed. So that's why we have to check that n is greater than 30. In this case, we know they're normally distributed, so it doesn't matter what size I pick. So again, sort of an interpretation. However, it does change the grouping of the way I do my chart, because it is still, I'm only still picking small sizes, so it is going to change that range, and it's going to consolidate it, it's going to condense it, it's going to squeeze the data, because I really only picked 4. So n is equal to 4. So again, our mean is going to be the same no matter what, which in this case is 135. What's going to change is my standard deviation, which is going to be 18 divided by the square root of 4. Square root of 4 is equal to 2, so 18 divided by 2 is 9. So basically, I've taken the same curve. I still have the average of 135, but this time, instead, it might even be easier if I draw on here. So instead, this time, I'm going to have a square along here. It's going to be steeper. So this inflection point is half of what it was. So instead of at 135 plus 18, it's going to be 135 plus 9. So my one standard deviation now is squeezed in closer to that data. It's squeezed in closer. This would now be 144, 135 plus 9. 135 minus 9 is 126. So it's squeezed the data. All right. What happens if I have to find a z-score? So I know that I have the central limit theorem that's going to apply, but I want to change a sample to a z-score. Remember, x bar is a sample x. But I have to change that to a z-score. Well, it's going to be a very similar formula. It's going to be x bar minus mu, but instead of just dividing by theta, we're going to do, or divided by sigma, we're going to do sigma divided by square root of n. So calculator is going to be real important on this one, so we put it in our calculator correctly. All right, figure shows the mean distances traveled by drivers each day. You randomly select 50 drivers, ages 16 to 19. What is the probability that the mean distance traveled each day is between these 2 miles? Right? Doesn't say anywhere that this is normally distributed, but because we have greater than 30, we're okay. So my mean is equal to I'm not sure why it's not ready again. It's like it's pausing on me. No, I'm going to pause for a second. All right, I think we're working again. So we randomly select drivers between 19 and 16 and 19 miles. So we're looking at this part of the chart. So the mean of my X bar is going to be the mean of my actual numbers, which is 20.7. Those two are the same. My standard deviation for the sample is equal to the original standard deviation divided by the square root of n. My original standard deviation is the 6.5 divided by my n, which we said was 50, square root of 50. If we did this correctly, we're going to get approximately 0.9 miles. So let's check our calculator. 6.5 divided by the square root, second x squared, so square root of 50 equals 0.91, or 0.92 if we're going to round it, but 0.9 is fine. Right. Then it says, what is the probability that the mean distance traveled is between? So again, here is this word between 19 and 22 miles. So between. Right. So again, this is the average age, and this is the average miles. So we're going to have to find Z1 and Z2. Remember, the largest minus smallest because it's a between statement. So Z1 is the largest, which is going to be the 22.5 minus the 20.7 divided by, now careful, that's 6.5 divided by the square root of 50. We want to leave it in this format for our calculator so that we can get more accurate an answer. Be careful, don't round too soon. So in my calculator, 22.5, oops, I need parentheses. So I already started it off wrong. So parentheses, 22.5 minus 20.7, the entire numerator in parentheses, divided by the entire denominator in parentheses, which is going to be the 6.5 divided by the square root of 50. Okay, close off your parentheses, hit enter, and we get 1.958 or 1.96. 1.96. Likewise, Z2 is going to equal Z2 is going to equal 19.4 minus the 20.7, so a negative number this time, divided by 6.5 divided by 50. Again, using your calculator, I'm not going to do this one, but use your calculator correctly. Make sure you get the right answer, negative 141. Now I'm going to go to the normal standard. Normal CTF of negative 10,000, whatever you're putting in, to 1.9601, and I'm going to get 0.9750. For the red one, if I type in normal CTF 10,000 negative 1.41, 0, 1. I end up with 0.0793. If I subtract these two, what is this? Move it a little bit so it'll fit better. And that equals the 0.0793. Subtract these two, and I end up with 7, 5, 9, 8, and that will be my answer. So the probability that the mean distance between each traveled each day is between 19.4 and 22.5 is 89%. So most of the time, almost 90% of the time, you're going to pick a person whose travel distance is between 19 and 22, 19.4 and 22.5. All right. So, one more. All right. It says the mean room and board expense per year at a four-year college is this amount. So the mean is equal to 10,453. You randomly select 9 college students. What is the probability that the room and board is less than this amount? Also, assume the room and board expenses are normally distributed. So the fact we're picking 9 is okay. And the standard deviation is 1650. We want probability that the mean is less than. So we want our x bar to be less than 10,750. Which is good because less is left, so we're not going to have to do any converting. So the mean of the x's is still the 10,453. The standard deviation is the 1650 divided by the square root of 9, which is equal to 550. My z-score is going to equal the 10,750 minus the 10,453 divided by 1650 divided by the square root of 9. If I do that correctly, I end up with 0.54. So the normal CDF negative 1,000, 0.54, 0, 1 equals 0.7054. This is greater than 1, so again it should be more than 50%, and it is, so that's the way you can sort of check yourself. You can see that we're just doing the same thing over and over and over again. In this section, really the only thing that's changing is using this formula when we talk about lower numbers or using the central limit theorem. All right. Last one. Some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed with a mean of 1615 and a standard deviation of 650. So the mean is 1650, standard deviation is 550. All right. What is the probability that a randomly selected college student who uses a credit card to pay for school-related expenses pays less than $1,400? All right. This one is we don't have to worry about anything because it doesn't mention anything about sampling. So this is back in section 5.2. Doesn't mention anything about sampling people. Just says, here's what we got. So in this one, Z is calculated the normal way. Mean with X minus the mean divided by standard deviation. So no alterations. So that would be, in this case, X pays less than, so X is less than 1,400. So we would have 14 minus 1615 divided by 550, which is equal to approximately negative 0.39. Normal CDF ends up equaling 0.3483. So what is the probability? So the probability of selecting a student whose pay is less than 1,400 is equal to 0.3483. That's the probability. All right. Number 2, now we randomly select 25 students. We randomly select 25 students who use the credit card. So now this one says we are going to need to use the other formula. So this time my Z is going to equal the X bar minus the mean divided by standard deviation divided by square root of n. So that's going to be the 1,400, still less than, so 1,400 minus 1650 divided by 550 divided by the square root of 25 is approximately 1.95. Negative, sorry. So this time if I do the normal CDF, I end up with 0.026. So the probability this time is 0.0356. So compare the differences between 1 and 2. So this is what it says. So this is your interpretation. There is a 35% chance that college students will pay less than $1,400 with their credit card. And there is a 2.6% chance that when a sample of 25 students that person, so the one you chose, that person will pay less than 1,400. So 35% chance that any college student pays less than $1,400. But if you take a group of 25 students, so you just randomly select 25 students, that percent drops all the way down to 2.6. because of the adjustment made. So as a result, we have to account then for the fact that this sample is not as predictable as reality. Reality is much more predictable. Therefore, we can say that this is unusual. Unusual. Because we're way back. The 2.6 is below that percent mark. Like I said, I know this section can be a little tricky. The biggest thing to remember is to look for certain words. Look for standard normally distributed. Just look for whether it's a sample that you're taking out of it. Look for some certain words. This will not be as heavy on your test as the other sections, so that don't let the wording get to you in that case. Alrighty, and that wraps up Chapter 5.